Now that you have the basic idea as to what an atom looks like, what an atom is made up of, and how to count atoms and how those atoms combine into different formulas, we're going to look particularly at electrons in atoms. And to start off with the electrons in atoms, we're going to have to look at the electromagnetic spectrum and talk about light and how that behaves, because that leads us right into electrons. So what you see here are two pictures of what people think the atom looks like. One on the left is a little bit earlier idea. One on the right is going to be the idea of actually what we think an atom looks like now, with the electrons clouds versus electron paths that are pictured on the left. So before we get these pictures, people just had Rutherford's model. And if we think back to the chapter before last, I know that's been a while, okay, was that Rutherford had the nucleus in the center and then the electrons spinning around the outside, which is pretty much how this picture here on the left looks. But it's not quite right because it didn't really explain the electrons and these negatively charged particles orbiting around a positively charged. Since negatives and positives attract, why weren't they pulled in closer to the nucleus? And we need to really figure out exactly where are these electrons. So they studied light and matter and then looked at some actual chemical flames and colors of chemical flames that we are going to actually look at in the lab later. And they decided then kind of what they think the atom looks like now. So we're going to start off with light. And properties of light. What exactly is light? Okay, well, from lots of different scientists over the years, we've come to realize that light is actually both a particle and a wave. So it's a little dot moving, and it's also then a wave moving. And we're going to talk a lot about this. So it's actually little dots, and then these dots that travel in waves, both a particle and a wave. Now, along with light, okay, and what exactly it is, there are many, many forms of light. Not just the visible spectrum, or the colors that you can see. And like I had mentioned just a minute ago, all of these forms of light, including the visible, are called the electromagnetic spectrum. Remember, that's all forms of light. I'm going to look at an example of the electromagnetic spectrum here in a second. We have the obvious visible light, okay? We also, though, have X-rays, ultraviolet light, we have microwaves, and many, 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 many others, okay? Now, when we look at light, light has certain characteristics, okay? And hopefully we have covered these in previous years, but I'll give you a little refresher, okay? Light actually has two characteristics. It has a wavelength, which is going to have a neat little sign here that I'll write in a second. And a wavelength is the distance between corresponding points on a wave. And the sign for a wavelength is what we call lambda. That's like that. Okay, kind of like a backwards hunched over H. A wavelength is going to be, here's my wave from this point to this point, or finish there, or from this point to this point. Corresponding points on a wave, okay? From my line to the X, then is not a wavelength, those are not the same point, okay? Well, the other characteristic of light, if I have a wavelength, I also have what's called a frequency. And I'll put the little sign in there in a second. And this is the number of waves that pass a point in a second. And it doesn't have to be a second necessarily, but we define frequency as being a second. It has a little nu. It's kind of like a V with a little bit of a curve. Okay. These frequencies are measured in seconds to the negative first. Remember, this negative first just means that the seconds is on the bottom, which means that I have the number per second. So notice how seconds is on the bottom. The number of waves does not have a unit. You just count them. Okay. And you can also measure it in what's called a hertz, which is Hz. Okay. Hertz. It's a hertz. Okay. And when we look at wavelength and frequency, okay, they are inversely proportional, which means that as one goes up, the other goes down. So if I have a really long wavelength, I have a really small frequency. If I have a really large frequency, I have a really short wavelength. Okay? So when we look, if I have a really long wavelength, which is a high wavelength, okay? So I have a large wavelength, I'm going to have a very small frequency, meaning that there are very few waves that pass a certain point in a second. Whereas if I have a very high frequency, I have a very low wavelength. And we relate these two together in an equation. It's a very easy equation. It's C equals lambda times nu, or frequency times wavelength. Okay, now what is the C? This C is the speed of light. And the speed of light is about 3 times 10 to the 8th meters per second. So what we get here is that all light travels at the same speed. As your frequency goes up, my wavelength goes down, but they go down and up proportionally, which means that I'm always going to have the same number as a speed for any type of light. Doesn't matter whether it's an X-ray, a gamma ray, a visible light, doesn't matter. Okay. So let's take a look here at the picture of the electromagnetic spectrum. I've got a couple different examples. Okay. So here I have radio waves all the way through gamma rays, and this one gives me a wavelength. Okay. Radio waves have a wavelength of about 10 to the third, or about 1,000 meters. And then as we go down, microwave, infrared waves, wavelengths get smaller. Okay. But these frequency numbers down here get bigger. So notice how these two numbers here are inversely proportional, like we just talked about. Okay. What I liked about this particular electromagnetic spectrum was that it gave some examples. And so if I have a building that's the size of a radio wave, or radio waves are the size of a building. Then we have human beings, then we have butterflies, and the point of a needle, protozoans, molecules, atoms, and a nuclei. So gamma ray wavelength is about the size of an atomic nuclei. Very, 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 very small. Okay, when we look at another type of electromagnetic spectrum, we see some more examples. Okay, football field, height of a man, a baseball, paperclip thickness, all the way down to subatomic particles. Okay. They give us more examples of these waves. Gamma rays again, X-rays, ultraviolet. Now here we have the visible, which goes from red to violet. And notice how they have different wavelengths. Okay. Then I have infrared, and let's notice here how the infrared is next to red, and the ultraviolet is next to the color violet. Like that on purpose. Then we have the radio spectrum, which is like the broadcasts, AM, FM. We also have cell phones, which operate on microwaves. And then you have some examples down here, which is why I liked this spectrum, of the different types of things that are at these particular wavelengths. You've got imaging, okay, you've got night vision, you've got dental, those little curing sticks they use if you ever have a cavity, okay, that's here in the ultraviolet. They have X-rays, you've got the baggage screening, suntan, that's all ultraviolet rays, those rays that when you go Tanning is like UVA and UVB rays. Okay, so just lots of examples of different things on the electromagnetic spectrum. Let's take a look now at your electromagnetic spectrum and answer these questions. So it says, what kinds of radiation have the longest wavelength? So we look at our table here. I find my wavelengths, find the ones down here. Which ones have the longest wavelength? The ones all the way on the left. That would be your radio waves. Well, which then have the shortest? Well, the other end of the spectrum. Down here, that would be my gamma ray. The next question then is, what radiation has the lowest frequency? Frequency. Remember, frequency and wavelength go opposite. So if I have a low frequency, I have a very large wavelength. And we see that here on the left. Low number compared to the ones on the right. So lowest frequency, that'd be my radio waves. Which radiation can be seen by the eye? Which ones can we see, or the only ones that we can see, are these ones in the middle with the colors. That's called our visible spectrum. Now we're going to sequence the different segments of the visual spectrum in order from shortest to longest. Wavelength. So the shortest wavelength is going to be violet. So you go violet, blue, green, yellow, orange, red. We leave out indigo. It's not really a color. Now sequence the types of radiation from lowest frequency to highest frequency. So lowest frequency down here, I have radio, and I have microwaves, and we're going to skip and do the infrared. Then I have my visible light, and I have my ultraviolet light, then X-rays, and then gamma rays. Compare the wavelength and frequency of each kind of wave. What is the relationship and what is the equation? I looked at this earlier. Remember that they are inversely proportional. And we already looked at this equation. That's that C equals wavelength times frequency. And then number 7 says, looking at the electromagnetic spectrum above, what is the speed of each wave? Remember I mentioned that. The speed of each wave is all the same. 3 times 10 to the 8th meters per second. So I'm going to calculate the frequency of a wave that has a wavelength of 699 nanometers. And this is one of those units that we haven't used a lot yet, but we will this chapter. And so we've got to remember what a nanometer means. Okay? So I have my equation, which is C equals lambda times nu. Okay? I know the frequency, and I know C, but I cannot just plug in the 699 because we're measuring C in meters, 3 times 10 to the 8th meters per second. Well, I can't have one of them in meters and one of them in nanometers. And I like to tend to change things to meters. So we're going to plug in our meters there when we get it. You're trying to remember how many meters are in a nanometer. Well, there are 1 times 10 to the 9th nanometers in 1 meter. Nanometers are very, very little. So if I have 699 nanometers, I have way less than a meter. Because in 1 meter, I have 1 times 10 to the 9th nanometers. So what am I going to do? I'm going to divide by 1 times 10 to the 9th. And I'll get 6.99 times 10 to the negative 7th meters. And that's the number that I'm going to plug in here. Now I'm good to go to solve for my frequency. So what am I going to do? I'm going to divide both sides by 6.99 times 10 to the negative 7th. Remember when we plug it in our calculator that we are putting in the E key, and I get a frequency of 4.29 times 10 to the 14th Our unit here is seconds to the negative first, or Hz, hertz, either one, doesn't matter. Using the same equation, why don't you go ahead and try the next one. You're just going to be solving for wavelength in this one instead of frequency. And you should get 652 nanometers.